Okay, so today's talk, I'll give on a research topic and current development. So it's basically based on the adjacency matrix and its eigenvalues. So this is a problem that is on reciprocal eigenvalue properties of graphs. So this problem actually started around 2005, and then the developments which has been done and how the questions were posed in between. Those I'll tell you so that you can learn how to move on a certain problem. So as I told, this is based on adjacency matrix and its eigenvalues. So background already, I think many things you know because about adjacency matrix you have read a lot of things. So I'll just again recall so that we can use certain fundamental properties. So let us take a graph, and I'm taking a simple graph again. So you have a adjacency matrix that has 0, 1 entries. So all the entries are either 0 or 1, and your diagonal entries, those are 0. Okay. So you have a matrix, which is a symmetric matrix, and also trace is 0. So positive eigenvalues are there, then negative eigenvalues are also there, and possible 0 eigenvalues can be there. So, for example, this example I had considered last in first class also. So this is a simple example, and you can see the adjacent symmetry. And throughout the talk, I'll use the polynomial also, and the characteristic polynomial will be a monic polynomial. So the first coefficient is 1, and the last coefficient also, you know, Cn, that will be the determinant of the matrix. And I think you have also read like these coefficients can be calculated using spanning linear subgraphs. Okay. So this C1 is nothing but it will always be 0. And then C2 is the number of edges. So those can be means negative of the number of edges. So those can be computed looking at the graph or taking from the adjacency matrix and its eigenvalue. So this matrix, about this matrix, because this is the first matrix that was related to or associated to a graph. This has certain properties like those I think you have already gone through, or you can observe. These are the very what I say, like very fundamental but very interesting things that the matrix tells itself about the graph. So if your graph is simple, you already know that the matrix is symmetric and with zeros on the main diagonal. And then if you go further, so as I told, if I take sum of all entries in the matrix, it's telling you how many edges are there. So it's 2 times the number of edges. So looking at the matrix itself, this is like you can say, obviously this is a very trivial thing, but you can say how many edges are there in the graph. Third thing is if I take all 2 cross 2 principal minors, that will give you the coefficient also, the C2 in your characteristic polynomial, the coefficient of x to the power n minus 2. That is the number of edges with a negative sign. So this I think already you have computed in register class. So this is also you are getting from the matrix. You can say how many number of edges. And third thing is if I take all 3 cross 3 principal minors and then add them, I'll get twice the number of edges in the graph. Okay. And twice the number of triangles in the graph. Okay. So how many 3 cycles are there in the graph? You can get if you take all the 3 cross 3 principal minors and add them. And this is a result that we were using also, we had used. So this is saying that if you take ag to the power k and look for the ijth entry, that gives exactly the number of walks of length k from I to j. Okay. So this is again a very classical result, and it tells much and very much useful also. So these 5 things that I wrote here, these are the things like looking at the adjacency matrix, I can say about the graph structure. Okay, how much I can say just looking at the entries. And if I go for the eigenvalues, so if I calculate the eigenvalues, as you observed, it's a symmetric matrix. So all the eigenvalues are real numbers, and I can arrange them like lambda 1 to lambda n. So lambda 1 I'm taking here smallest, and the lambda n is the largest. Lambda n, because the matrix is symmetric, you know that this is the spectral radius of the matrix, and we denote it by rho j. And I'll say that the graph is non-singular when AG is non-singular. So AG can be singular also, determinant can be 0. So when it's a singular, AG is singular, I'll say that the graph is singular. Otherwise, the graph is non-singular. And by eigenvalues of G, because I'm using in this talk only adjacency matrix. So when I'll say that eigenvalues of G, it's basically I'm saying eigenvalues of AG. Okay. Now looking at the eigenvalues, if I look at the eigenvalues, then obviously you have observed that trace is 0. So positive eigenvalue is there, then negative eigenvalue is also there. So for this example, you can see this is the spectral radius 2.2170. And you have also negative eigenvalues. And the red mark I have put to one eigenvalue, that is the smallest positive eigenvalue. So the least eigenvalue, that is the negative one, that is minus 1.481 for this graph. This has also connection with the graph structure. The spectral radius is connected to graph structure that decides how much connected. Like in your Laplacian case, the algebraic connectivity tells about the connectivity of the graph structure. But in adjacency case, because Laplacian is just diagonally perturbed, the adjacency matrix is diagonally perturbed. So how the smallest eigenvalue of Laplacian behaves, that means leaving the 0, so the algebraic connectivity. A similar way the spectral radius behaves here. So these eigenvalues are important. Eigenvalues, those are studied. But if I know all the eigenvalues, what I can say about the graph structure. So if I add all the eigenvalues, you already observed that trace is 0. So sum of all eigenvalues is 0. But if I take squares of all eigenvalues and add them, so that will give you 2 times number of edges. That's because this is, if I am taking squares of all eigenvalues and adding, so basically I am taking the trace of a square, and that gives the closed works of length 2 from each vertex to itself. So that will give you how many edges are there basically. So, and it will be calculated 2 times, because you can, from 1 to 1, you can do twice like that. So this is 2 times the number of edges. So that will be the sum of eigenvalue squares. And if I take the lambda 1 q to lambda n q, and then I'll add them. So that will give you 6 times the number of triangles in the graph. Okay. So this way, looking at the eigenvalues, if I know the spectrum, I can say these things about the graph structure. So how many 3 cycles are there? How many edges are there? And similarly, if I know lambda n minus 1, and that's equal to minus 1, then it will tell that it's a complete graph. Okay. So this is, again, through this only you can prove that Kn is determined by the spectrum. Actually, complete graph is determined by the spectrum because it has the second largest eigenvalue minus 1. Okay, that way one can prove also. So if it's exactly minus 1, it's you can say that it's complete graph. And if it's 0, you can say that the graph will be completely multipartite. Okay, complete multipartite graph. Similarly, if I go for the third largest eigenvalue, if third largest eigenvalue is strictly less than minus 1, then you can say that the graph is nothing but it's isomorphic to P3. So only for P3 this happens. So if the third largest eigenvalue is less than minus 1, the graph must be isomorphic to P3. Similarly, if third largest eigenvalue is equal to minus 1, the complement of the graph is isomorphic to the union of complete bipartite graph with some isolated vertices. So these things these are very simple or preliminary results, and few of them I have listed here, but there are many that looking at the eigenvalue you can say about the graph structure. Similarly, if you look for the spectral radius, as I told, spectral radius is much more connected to the connectivity of the graph. So here you can see, observe that in case of tree, spectral radius is the minimum when it's a path, and it's maximum when it's a star. And in between any tree you are taking, so spectral radius will lie between the spectral radius of Pn and Sn. Okay, and these inequalities, those will be equality only when this happens. So Pn is the with the least spectral radius, and Sn is the with the largest spectral radius. So that happens. So spectral radius, from this you can observe that spectral radius is closely related to the maximum degree of the graph. And it's like when spectral radius is large, you can say that there are highly connected vertices. That means there are vertices with large degree. So this way, graph eigenvalues, they are related to graph structure. And this is one result that you know, that how to characterize bipartite graph. So bipartite graph, you know already the definition, I think. So a graph is bipartite if you can partition the vertex set to two subsets, and all your edges, possible edges, are between if your parts are A and B, then those edges are from A to B. So there is no connection between the vertices in one part. So that's a bipartite graph. So bipartite graph examples also, you know, like stars are bipartite. Now, one way of looking at or deciding whether a graph is bipartite or not, that is, you have to look at the cycles. So if the graph has no odd cycle, then the graph must be bipartite, and this is a if and only if condition. So this is a way to decide whether a graph is bipartite or not. And that's important because of in computer science, like many graphs they use are bipartite graphs or trees. So to decide a graph is bipartite or not, it is important. So this way, you can check that there is a odd cycle or not, then it can be told that it's bipartite or not. But this is not easy also. You have to use algorithm, and then sometimes it takes time. But there is this nice result that is known as a spectral characterization of bipartite graphs. And looking at the eigenvalues, you can say whether the graph is bipartite or not. So a graph will be bipartite if and only if negative of each eigenvalue is also an eigenvalue with the same multiplicity. Okay, so this I think Rajesh sir has proved already. So if the spectrum is symmetric about origin, then the graph must be bipartite. So this is a if and only condition. This is known as the spectral characterization of bipartite graphs. But you don't have to check for each eigenvalue. This is a final result that you can just look for that. If the negative of the spectral radius is one eigenvalue, then you can conclude that the graph is bipartite. So you don't have to check for each eigenvalue. So look for the spectral radius. If you can compute the spectral radius, the largest eigenvalue, and the negative of that eigenvalue is also an eigenvalue, then you can conclude the graph is bipartite. Okay. But this again, calculating, like the first thing I told, that you have to use algorithm, and you need for large graphs, you need computational way to check whether it's a bipartite or not, because you have to find out whether there is a odd cycle or not. Second one is you have to check the eigenvalues. So computing eigenvalues, again, not easy. Even to calculate the spectral radius, it's not easy. So computing eigenvalues means you are solving a polynomial and finding the roots, and that's a difficult problem again when the number of vertices is large. But nicely, if you look at the next result, This is saying that a graph is bipartite if and only if all the odd coefficients in the characteristic polynomial are zero. So basically looking at the characteristic polynomial, you can decide whether the graph is bipartite or not. So if in the characteristic polynomial, all the odd coefficients, they will vanish, then you can say directly it is bipartite or not. So and this is the last one is most useful. Like you can use this because just calculating characteristic polynomial is not a difficult thing. So this way you can know. Now, if your graph is non-singular, like if the determinant is not vanishing, that means all the eigenvalues are non-zero. And let us take the graph is bipartite. Then the spectrum looks very nice. Like you already observed that it's bipartite. Then if lambda is an eigenvalue, then minus lambda will be eigenvalue. So, and you are taking non-singular, so you are avoiding all the zeros. So your spectrum is just, half of the eigenvalues and the other half are with negative sign. And this way the spectrum look like. So it's like half of the eigenvalues you have to compute.
Excuse me, ma'am.
Yes.
The meaning of odd coefficient is just the coefficient of odd powers.
Yeah.
Okay.
Ma'am is odd. Then highest degree power also sometimes coefficient may be zero.
Oh, what?
Means odd coefficient in that odd coefficients of this characteristic polynomial zero.
Uh,
That means that if n is odd, that time
Here you look at the characteristic polynomial. It starts with x to the power n.
C
Okay.
zero, that is C zero. Okay.
So,
That should not be zero. Okay. Thank you.
so C1 is always 0 and the next one you are looking for. So basically you are not getting odd cycle, means you will not get linear subgraph of size, odd size. So those coefficients will vanish when the graph is bipartite. Okay.
Yes, ma'am. Yes.
Mm. Okay, so now just look at these two simple like examples. So here I have taken P2 and P4. Yeah, P4 I drawn in this way because of certain reason. But anyway, this is P2 and this is P4. Okay, so for P2 you know the spectrum and that is -1, 1. Okay, for P4 I have computed here. You can also calculate. So the spectrum will be like this. And both are bipartite graphs. So that's why if one is there, the -1 will come out. Here, like 1 plus root 5 by 2 is there, then its negative is also there. And -1 plus root 5 by 2 is there. So its negative is also there because they are bipartite entries. So now another thing you can observe, in the first one it's happening, but it's a trivial one, so you are not able to see. But in the second one, like if you compute or if you just look at the numbers, 1 plus root 5 by 2 is one eigenvalue, but it's reciprocal. If I look at the number, that will come out as -1 plus root 5 by 2. So this number is there and its reciprocal is also there as one eigenvalue. Similarly, this number -1 minus root 5 by 2 is there, but its reciprocal is this number, that is 1 minus root 5 by 2. And that's also present here. So in this case, like if one eigenvalue is there, its reciprocal is also present. Similarly, here also it's happening, like 1 is there, then a reciprocal of 1 is also 1, that is also present. And -1 is there, its reciprocal is -1, that is also present here. Okay, so these are the two graphs. Here you can see it's not like that only like lambda is an eigenvalue, then minus lambda is appearing. It's like lambda is an eigenvalue, then 1 by lambda is also appearing in the spectrum. Okay, so this we had observed, and then we thought about like, can we see and can we characterize the graphs? Like for when you are taking like when the spectrum is behaving like this, if lambda is an eigenvalue, then minus lambda is an eigenvalue. In that case, you know that which are those graphs, and those graphs are the class of all bipartite graphs, right? So here we pose the question like, if you are taking a graph, like if you are thinking about this concept that can there be a graph with the spectrum in this way that if lambda is an eigenvalue, then minus 1 by lambda is also an eigenvalue. Okay, so this question was posed. So characterizing all the graphs that satisfies the property that the reciprocal of each eigenvalue is also an eigenvalue. Okay, and such graph exists that I have already given example P2 and P4. They are the graphs which are satisfying this property. So what we observed that it may happen that lambda is one eigenvalue, then 1 by lambda will be one eigenvalue for each lambda. But they may have the same multiplicity for each lambda, or the multiplicity may vary. Okay, so that can happen. So we define in two ways. A graph is said to have the reciprocal eigenvalue property or property R if lambda is an eigenvalue implies 1 by lambda is also an eigenvalue. But if we look at the multiplicity, like in bipartite case, multiplicity was remaining same also for lambda and minus lambda. So here if we restrict for each lambda, 1 by lambda is an eigenvalue, but with same multiplicity, then it's known as the strong reciprocal eigenvalue property. So this way we defined that property R and property SR. Okay. And later we observed that property SR, which is like lambda is one eigenvalue, then 1 by lambda, and with same multiplicity for each lambda. This property was already defined as property C by Ketkovic and others. So that was defined in 1978. And similarly, the property SR was termed as symmetry property by Godsell and Meike. That was also done in 1978. But the characterization of graphs was not done. They had used, in case of trees, to construct certain graphs. That way, these things were connected. So, looking at after defining, so our main problem was to characterize all graphs with property R, characterize all graphs with property SR. And before going to the characterization or the work done, I need two definitions. So those are important here. One is perfect matching. So matching in a graph is a collection of disjoint edges, and a perfect matching is matching in a graph is a collection of disjoint edges which cover all the vertices. Okay, so like here, if I look at this graph in this example, then if I take all the red edges, this gives a perfect matching because this covers all the vertices. So you have 8 vertices and you are choosing 4 edges. So basically all the vertices are covered. And this is the only perfect matching you can see, because there are 3 pendant edges, and for the pendant edges, I have to choose those edges because otherwise the pendant vertices will not be covered. So 1, 2, and 4, 5, and 7, 8, those should be chosen. Okay, and then the only option remaining is the edge 3, 6. So this is the only matching here, perfect matching here. So some graphs have a unique perfect matching like this graph. Okay. But in general, a graph can have more than one perfect matching. Like if you take a cycle of order 4, you can have 2 perfect matching. So like that. But in case of trees, if there is a perfect matching, then it must be unique. Okay. And such trees are nothing but non-singular trees. So if there is a perfect matching, the tree must be non-singular. That's a if and only condition. But for graph case, more than one perfect matching can be. And there are graphs there are with no perfect matching also. But if a graph has a unique perfect matching, then that graph must be non-singular. So that can be proved easily looking at the characteristic polynomial. Okay. So the way you are calculating the linear subgraph, so that way you can use, and from that result you can prove that a graph has a unique perfect matching, then determinant will not be zero. Okay. because that will give the corresponding linear subgraph, and you can add, and then you can show that the determinant is not zero. So this is a graph with a unique perfect matching. So I can say that its determinant will be not zero. So there will be no zero eigenvalues here. Okay. Another definition from here also I need alternating path definition. So alternating path you can define in many ways, like considering. So here what I am considering, I am taking a path, and it will be called as alternating path if it starts with a matching edge, and then like another edge, next edge should be non-matching, and then matching edge, then non-matching edge, but it ends with a matching edge. Okay, so then we call it that path as a alternating path. So like here in this example you can see, like if I take a path from 1 to 2, so that starts and ends, starts at 1 and ends at 2. So that uses only one matching edge. So that's the alternating path, because that is a trivial one. So it starts and ends with a matching edge, and there are no other edges, so we don't have to think about. But if I go from 1 to 6, okay, so then I'll use 1 to 2, 2 to 3, and 3 to 6. So then I'm starting with a matching edge, then non-matching, then matching. So 1 to 6 in this way, 1, 2, 3, 6, that's the alternating path. Okay. But if I go from 1 to 4, so I'll go from 1 to 2 starting with a matching edge, but then non-matching, then 3 to 4 is again non-matching. So that's not an alternating path. Okay. So alternating path, as I told, I can define in this way that it's just alternating, then also alternating path. It can start with a matching edge or non-matching edge. But here for this talk, I'm taking alternating paths which are starting at a matching edge, ending at a matching edge. Okay, so then the length of the alternating path will be always odd. Okay, so you'll start with a matching edge, then non-matching, then matching, like this. So always the length will be odd length. So for alternating path. Now this operation is important, that is corona of two graphs. So corona operation is defined between any two graphs. Here I'm taking the second graph as a pendant vertex, or you can say, sorry, isolated vertex. So this is defined in this way: take a graph and just add pendants to every vertex. Okay, then it's known as a corona. Like here I have P4, and then if I add pendants to every vertex, so I'll get a graph like this. So that's a corona of P4. You can also observe that P4 is nothing but corona of P2. And P2 is nothing but corona of K1. Okay. So I'm taking this is known as simple corona. So your second graph is basically K1. So this is the simple corona I'm defining. So just take a graph and add pendants to every vertex. Then it's known as corona or simple corona. This operation I'll use here, because this is one of the important operation that is related to these graphs with reciprocal eigenvalue property and its characterization. So when we move to characterize the graphs with reciprocal eigenvalue property, this is the first observation you can say, or this is the first result that we got, and this is the result which is a more general result also so far, and that it's giving a large class of graphs which satisfy property SR. Okay, so take a graph and make its corona, like add pendants to every vertex. Then if lambda is an eigenvalue of the graph, then -1 by lambda also will become one eigenvalue of the graph. So that gives that if lambda appears, then -1 by lambda appears, and they will have a same multiplicity. Okay. So if you are taking a corona, then this thing happens that lambda -1 by lambda, this pair will come, and they have the same multiplicity also. And so if I take the graph G1 as bipartite, then G will be also bipartite, like the corona. And in that case, because this plus minus pairing is also there. So we'll get that if minus 1 by lambda is coming, then 1 by lambda will also come. So you will get that lambda is an eigenvalue, then 1 by lambda also eigenvalue, and they will have some multiplicity. Okay, so the graph will satisfy the strong reciprocal eigenvalue property. So if you are taking a corona of a bipartite graph, then it's satisfying the strong reciprocal eigenvalue property. And that's easy to prove because what you can observe is when you are making corona, you are just adding pendants to every vertex. So basically your corona of G1 will look like adjacency matrix of G1, adjacency matrix of the corona, that will look like a blocked matrix. Here you have to take adjacency matrix of G1, and then because you added pendants to every vertex, so this block will look like identity. Each row one will appear. So and then it's transpose here, that is identity, and here there is from the between the pendants there is no connection, so you will get here 0. So this simple adjacency matrix will come, and for this then we can check for eigenvectors and go for eigenvalues. So we can get that if mu1, mu2, mu_n are eigenvalues of G1, then you will get that mu1 plus mu1 square plus square root of mu1 square plus 4 divided by 2, and it's like a negative this pairing, like mu1 minus square root of mu1 square plus 4 by 2. This way, these two will come as eigenvalue. Okay, and both will have like eigenvectors also correspondingly you can construct, and you can observe that both will have some multiples. Similarly for all, so like this type of pairing will come. So if mu1, mu2, mu_n are eigenvalues, you will get these as eigenvalues. And this why I'm saying pairing, because this into this, if you multiply, you will get -1. So basically, if this is lambda, then this is -1 by lambda. And when you are taking the graph G1 as bipartite, so somewhere here again 1 by lambda is there. Okay, so you will have this result that if G1 is bipartite, then the corona of G1 will satisfy the strong reciprocal eigenvalue property. So this is the first result, and as I told, this is the largest class so far. We have got like satisfying property SR. Now, obviously, then the question is whether all graphs, like at the time now we know that there are other graphs, but at the time we asked question whether all graphs which are satisfying property S are their coronas, or there are other graphs. So we got examples like there are non-corona graphs which are satisfying property R and SR. So these are the two graphs. And this example I took for perfect matching. This has a unique perfect matching and non-singular. And this is another graph. This this has also a perfect matching, you can see. And these two graphs are not corona. Clearly, you can see here pendant is missing, here pendant missing. Similarly, this is also not corona. But both satisfy property SR. Here I have not written the spectrum, I have written the polynomials only. And like I'll tell how it's related to polynomial. So looking at the polynomial itself, we can decide whether the graph is bipartite with satisfying property SR or not. Like in case of bipartite case, looking at the polynomial, you can decide whether the graph is bipartite or not. Here also looking at the polynomial, you can decide whether the graph is satisfying strong reciprocal eigenvalue property or not. So here I have written the polynomials, but anyway, we'll go to that. So what we observed that is one class that is satisfying property SR, but also we observed that it's not easy to characterize all graphs satisfying property SR or R. So we looked for first the class of trees, and there we looked for which trees are satisfying property SR or R. Okay. So here first we observe this like one kind of thing is happening in the polynomial, and from the polynomial itself we can say. So first thing is I'll define this, that a polynomial, take any general polynomial. So a0 x to the power n like this up to n. So this is a degree n polynomial, and it has real coefficient, that will be called as self-reciprocal or palindromic polynomial if ai is equal to an minus I or I equal to 0 to n. Okay, in that case, basically you can observe your px is nothing but x to the power n p1 by x. Okay, then it's called palindromic polynomial. So coefficients will like ai equal to an minus I. And it is called anti-palindromic if px equal to minus x to the power n p1 by x. In that case, ai will be minus an minus I. Okay. And what place he proved that if alpha is a root of a polynomial that is either palindromic or anti-palindromic, then 1 by alpha is also a root of that polynomial and they have the same multiplicity. Okay. So if you are taking a palindromic polynomial or anti-palindromic polynomial, then if alpha is a root, then 1 by alpha will also be a root and they have the same multiplicity. Okay. And what we could prove that if you are taking a graph with property SR, let's say the polynomial is looking like this, then it will become like this way. Px will be minus x to the power p1 by x. And so you can conclude that Ci mod will be equal to Cn minus I mod. Okay, sorry, here also plus minus I have. This is a typo. So your coefficient there will be either Ci equal to Cn minus I or Ci equal to minus Cn minus I. So basically the polynomial will be palindromic or anti-palindromic. Okay. So if the graph is satisfying property SI, then the polynomial must be palindromic or anti-palindromic. And if it's anti-palindromic or anti-palindromic, then already place has proved that the polynomial has roots like lambda and 1 by lambda with same multiplicity, so it will satisfy property SR if you are considering characteristic polynomial. Okay, so in our examples that I gave, so here you can see that this polynomial is a palindromic polynomial. This polynomial is also a palindromic polynomial. So I conclude that both the graphs are satisfying property SR. Now, if this thing is happening, like the polynomial is palindromic or anti-palindromic, that means the coefficient, whatever Ci, its modulus is same as Cn minus I modulus, then what we can conclude that because your polynomial is a monic polynomial, so the determinant here, like if the graph is satisfying the strong reciprocal eigenvalue property, then this coefficient Cn, that is the determinant of the adjacency matrix, that will be either plus 1 or minus 1. Okay. And that can be observed easily because you are taking lambda one eigenvalue, then 1 by lambda also eigenvalue. So when you will multiply all the eigenvalue, that is your determinant basically, and they are appearing with same multiplicity. So obviously the product will be plus 1 or minus 1. Okay. So if G is satisfying strong reciprocal eigenvalue property, then determinant will be plus 1 or minus 1. That is clear as per definition. But when the graph is satisfying property R, that means your multiplicity may be different for lambda and 1 by lambda for certain lambdas. Then this is a question whether the determinant will be plus 1 or minus 1 or some other number it will take. Okay. But in case of property SR, this will be 1. And also, since C1 is 0, so Cn minus 1 will be 0. And C2 is negative of the number of edges that you know. So Cn minus 2, that will be the negative of the number of edges, or positive means the number of edges, because this modulus should be same. So these are the things we can say now, because certain coefficients we know that what are they. So accordingly, the like this side if you come, those also known to. So you don't have to calculate the large principal sum matrices, like it's their minors and you have to add this. You can calculate from this side also. Okay, so the coefficient they will match like this. Okay, so from this, like looking at the coefficient, so using that result like for coefficients and the characteristic polynomial, you can prove that if you are taking a tree, and T will satisfy property SR if and only if it's a coronary. So if it's a coronary, then it satisfies property SR. That's by our first result. So if I'm taking a coronary, then obviously any corona you are taking that satisfying property SR if the graph is bipartite. So you are taking a tree and that is a corona tree. So that's bipartite. So that will satisfy property SR. But the other way it holds also. If T is satisfying property SR, then it must be a corona. Okay. And that you can prove using the characteristic polynomial or whatever we observed, how it's behaving. So looking at that, you can prove. And here I am telling how it has been counted. So as I told, C2 is the number of edges. And that will be equal to either that will be equal to C2k minus 2 with a negative sign or just equal to C2k minus 2. So we'll just compute these two numbers. And if it's not a coordinate tree, we'll prove that these two numbers will not match. So if T is satisfying property SR, we'll show that T must be a coordinate. Okay. So if I take it's not a corona, I'll show that these two coefficients will not match. Okay. These two numbers will not match. So let us take a tree and that is not a corona tree. So I'm assuming that it's satisfying property SR, but I have to show that T must be a corona tree. But I'm thinking that let's say it's not corona. If it's not corona, then somewhere in between, like you can see that this situation would be there. The graph is satisfying property SR, so it has obviously even number of vertices. And now I'm thinking that it's not a corona, so you will get like this, like some vertices are there, some at least two vertices will be there, which are not with pendants. Okay, if every vertex has a pendant, and then it's a corona. So I'm assuming it's not a corona, so I'll get a situation like this. So two vertices would be there where there are no pendants. Okay. Okay, at least two because the graph has even number of vertices. So at least two vertices would be there where pendants are not there. So this kind of situation would be there. Now, because the graph I'm taking is satisfying property SR, it's a non-singular graph, okay? So T is non-singular, so T has a unique perfect matching, okay? So I took the matching edges, let's say these are F1, F2, and Fk. So T has 2k number of vertices, so it has I'm considering the k edges. So those are which are the matching edges. Okay. So it has 2k minus 1 edges. So the k edges, matching edges I have drawn here. Okay. And I also have a situation like this where two vertices are without pendant vertices. Now I'll count the numbers. C2 is the number of edges, so that will be exactly 2k minus 1. And C2k minus 2 will count. So C2k minus 2, as you know already, I think you have read already. That is nothing but you have to count the number of pairwise disjoint edge subsets of size k minus 1 because you are looking for linear subgraphs with your size 2k minus 2. Okay, so you will look for k minus 1 independent edges and those type of subsets you will calculate. Okay, how many such subsets are there? So I have to take k minus 1 edges. So there are already k matching edges I have drawn like this. So to count how many k minus 1 edge subsets I can make, so what I'll do, I'll just take k minus 1 matching edges from these k matching edges. So that will give me like that kind of subsets I'll make. So that will give me like I have to leave one edge and then other k minus 1 edges I have to take. So from the matching edges, k matching edges, I can form the like sets with k minus 1 pairwise disjoint edges. Those how many sets I can make? I can make k subsets, right? So to choose k minus 1 edges from these k matching edges, so I can make in k ways. So those will contribute k subsets of like disjoint edges of size k minus 1. So that will be the first number that is coming k. And now what I'll do, I'll just look for the non-matching edges also. So each non-matching edge that is adjacent to two matching edges. Okay, because tree is connected. Okay. So what I'll do, I'll choose a non-matching edge like this here, A1, A2. And this is adjacent to two matching edges. Those two I'll leave and the other edges I'll choose. Okay. So then I'll get a k minus 1 subset again. So this way I can also, because these non-matching edges are like how many they are k minus 1 in number. So each one I'll choose, and the edges which are incident, two incident edges which are matching edges, those I'll leave, the other edges automatically I'll choose. So that way I can get again k minus 1 number of subsets with pairwise disjoint edges. Okay, so this will give me k, and then the second way I can count as k minus 1. And then because this kind of situation is there in the graph, that you have a matching edge, then non-matching, then matching, then non-matching. Here there is no pendant, so those edges are not selected. So the situation in the graph will be like this. So in that case, what I'll do, I'll choose this edge, one edge, and this edge one edge, and then the rest edges I'll take as matching edges. That will give me another k minus 1 subset of edges. And so that will give me at least one such kind of thing. So if it's not corona, then this kind of situation would be there in the tree, and that will increase your counting of the number of like edge subsets containing k minus 1 edges. So then this C2k minus 2, this coefficient will be bigger than your C2. Okay, so that will contradict that your polynomial is not like that. So that's not as tree satisfying property SR. So if T is satisfying property SR, T must be a corona tree. It cannot be a non-corona. So that can be proved. So I hope you got, otherwise you can go through this paper. It's the same thing here. I just taken the picture and just I gave you, but it's written clearly how it's counting has been done. So it's a easy thing. And so this way we could prove that if T is satisfying property SR, then it must be a corona. Okay, so then in tree class, the characterization of all trees satisfying property SR is done, and that's the class of all corona trees. Okay, but then we looked for whether there is a tree which is satisfying property R, and that's not a corona because this is for SR. But there can be trees which are with property R, that means multiplicity may not match. So that may not be a corona. So here I'll use the inverse concept, because you can observe that this reciprocal eigenvalue property concept that's related to inverse graph inverse. Graph inverse is defined in this way, that if you are considering a non-singular graph, that means AG is non-singular. So always we can then we can ask for like what is AG inverse. Okay. So AG inverse will come out, and if your determinant will be determinant is plus minus 1, then AG inverse will have integer entries, but it can have negative entries also. But so this way God will define the inverse, that if there exists a signature matrix, that means signature matrix is a diagonal entry, diagonal matrix with diagonal entries plus 1 or minus 1, and its inverse is itself. So if there exists a signature matrix S, such that if you take S AG inverse S, that is non-negative. That means AG inverse is signature similar to a non-negative matrix. So then we say that G is invertible. And this matrix, as I told, this can be one integer matrix, or this can be with other numbers. But like if this is non-negative, then obviously we can associate a graph with it, this matrix, and that can be weighted, because if it's not with plus minus 1 entry, then that can be a weighted graph. So that graph is known as the inverse graph of G, and we denote it by G inverse. So given a non-singular graph, its inverse may exist or may not exist. It will depend on whether AG inverse is signature similar to a non-negative matrix or not. If it happens, then we can associate a graph to it. This will be the adjacency matrix for that. And that graph is known as the inverse graph of G. So it's G inverse. And in many cases, you can see that AG inverse will be a 0 plus 1 minus 1 matrix, and it becomes like a signature similar to a non-negative matrix. And so in that case, basically it represents a graph, and this matrix becomes the adjacency matrix. Okay. So here you have one example, like this is your G, and G inverse will be this. So here I have taken a unicyclic graph, but its inverse is a tree. Okay. So it can happen also. Now, the question which was posed in 1985 by Gottschall was characterize all the graph G so that G inverse is isomorphic to G. Okay, so that means G inverse exists and G inverse is isomorphic to G. So what are those graphs? That was the question. And what we did when we were proceeding towards characterizing graphs with property R, we first described how the inverse looks like. So all the entries of AG inverse we described for a bipartite graph. So, and with a unique perfect matching. So if G is a graph and that is a bipartite graph, and it has a unique perfect matching, say M. So you have like, then in that case, basically G has even number of vertices, and you are taking all the matching edges, that is the set M. Okay, so you have a unique perfect matching. In that case, if you are calculating AG inverse, you can describe each entry combinatorially, means looking at the graph. So what will be those entries? Those entries will be like a summation over all the paths. Those are alternating paths between I to J. And you will calculate this quantity, minus 1 to the power, the length of the alternating path. As I told, length is always odd. So this number will be like you can calculate. So this minus 1 to the power this, so this will contribute plus 1 or minus 1, and then you have to take a sum. Okay. And 0 if there is no alternating path between I and J. Then you will get Bij in this way. And Bij is nothing but the ith entry of your AG inverse. Okay. So you don't have to calculate AG inverse like computationally or the way inverse. You can describe each entry looking at the number of alternating paths in the graph. Okay. So this was the description that we'll use to prove the other results also. So this way, the inverse of a the adjacency matrix of a graph, which is bipartite and with a unique perfect matching, so we can describe. Okay. Now using this, like here, one example is given. So if this graph, this is a tree and this has a unique perfect matching, this is the matching, red edges are the matching edges. Okay. So now if I want to check like in the inverse, I want to check. So in the inverse, like I can say that between 1 to 2, there will be one edge, because 1 to 2, there is one alternating path, and that's the unique alternating path. So the sum will be whatever the entry you will count here, that will be plus 1 or minus 1. So this is the entry. So and then you can say that there will be one edge between 1 to 2 in the inverse, and that's happening here in the inverse. Similarly, there is one alternating path from 1 to 4, and because it's a tree, so that is the unique path. So when I'll calculate the Bij or B14, that will be plus 1 or minus 1, non-zero. So I can say that from 1 to 4, there will be one edge in the inverse, and that's there. Okay. And between 1 to 3, there is no alternating path. So 1 and 3, they will not be adjacent in the inverse. That is clear. Similarly, you can draw. So from the graph, if you have a unique perfect matching, you can look for the inverse, and you don't have to compute. You can, this way also, you can draw the graph. Now, this is the first observation that we got. that if you are taking a non-singular tree, then AT inverse like you will look for the adjacency matrix AT, and its inverse that will be diagonally similar to the adjacency matrix of some graph. So it's becoming like a signature similar to a non-negative matrix, and not only that, it's becoming a 0, 1 matrix. So it's a adjacency matrix for some graph. Okay, so it's happening for any non-singular tree. AT inverse is giving you the adjacency matrix of some graph. So inverse exists in that case. And the second thing that we observe is if you are taking any non-singular tree, T inverse must be connected. So first result is saying that T inverse exists. And T inverse, second result we got is T inverse must be connected. Okay. And later what we observe that T inverse must be bipartite. If T is a non-singular tree, then T inverse must be bipartite. Okay. And then other when we worked, then we got that these all are equivalent actually when you are considering non-singular tree. So if T is a non-singular tree on 2k vertices, okay, when it's non-singular, obviously number of vertices will be even. So if you are considering a tree which is non-singular, then all these conditions are equivalent. So T is satisfying property is then we already had proved that T must be corona. But also in that case, if T is a corona, then T will satisfy property R, that also we had proved. But if T is satisfying property R, then T must be also corona. So in tree case, these two properties like strong reciprocal eigenvalue property and reciprocal eigenvalue property, those are equivalent. So if the tree is satisfying property R, it must satisfy property SR. That means multiplicity must be same. And this class is also the class which Godsell was looking for. So that graph whose inverse is isomorphic to itself. So here in tree case, if you are taking a corona, then T inverse is becoming a tree and T inverse is isomorphic to T. Okay. And this is the number of alternating paths if I look at in T, that is exactly 2k minus 1. Okay. So all these conditions are equivalent. So for our purpose, we can observe that in tree case, property R and property SR both are equivalent. And the class which satisfy property R is nothing but the class of corona trees. Okay. So then in tree case, the problem is completely solved. And then we looked for unicyclic graphs. Okay. So we just unicyclic graph means you have to take a tree and just add one edge. So that is unicyclic graph. So here, when we observed, here again the questions are if G is a unicyclic graph with an even cycle and it's a simple corona, then it will obviously satisfy property as by our past result. Okay. So if you are taking a bipartite graph, that means I am taking even cycle. So bipartite and it's a corona, so it will satisfy property as well. Then whether the converse is true means is there a unicyclic graph which is not bipartite? Unicyclic graph with property SR which is not bipartite and it's not a corona. So these questions are there. Because in tree case, everything became corona. So then here, like, we asked these questions. What we observed is if you are taking a unicyclic graph with property SR, okay, then the cycle length, if it is G, that means the girth is G. It came out that if the graph is satisfying property SR, then G must be even. So the graph must be bipartite. Okay. So the cycle length should be even. So that is the first observation that we got. That if there is a unicyclic graph satisfying property SR, that must be a bipartite graph. Okay. And then we started with like bipartite unicyclic graphs with property SR. So what we observed, like if you are taking the graph, so obviously the cycle length can be 4 or more than 4. Okay. So if it's more than 4, that means G is not equal to 4, then we observe that that must be a corona graph. Okay, there is no other graph. That must be a corona. Okay, but if it's with got 4, then it can be a corona, or it can have certain other structure. Those are the 4 kind of structure that we have described. 3 classes are described here, and 1 class is described here. So that type of structure the graph will take, and that structure also constructed using coronas only. If you look at it's unicyclic, so there is a 4 cycle, and then some tree structures are attached, and they are very much similar to they are obviously corona kind of trees are attached. Okay, so this is the situation that G is a unicyclic graph with property SR. Then this thing will happen. Either it's a corona, or if it has a 4 cycle, then it will become like corona or such kind of graph structure. But the complete characterization is not known. We have described in this way, but the complete like characterization it's not done. Now this problem is still open, like here only for strong reciprocal eigenvalue property this classification is done, but for reciprocal eigenvalue property, like if G is satisfying the reciprocal eigenvalue property and it's unicyclic, the characterization is not yet done. This is still open. Now, if I look for bipartite graphs, other classes, so in certain classes, the things were studied. So one such class is, I would like to tell here. So here, we'll start with a bipartite graph with a unique perfect matching. So if we have a bipartite graph with a unique perfect matching, so it will look like this. So I have taken one example, let's see. So now what I'll do, I'll use one operation that is contraction of matching edges. Okay. So your matching edges are like this. Now what you'll do, each matching edge you just contract, means you identify the end vertices to a single vertex. So this edge you are deleting, and then both the vertices you are just identifying. So this way, what you will get, like from this graph with a perfect matching, unique perfect matching, you will get another graph. Okay. So with half number of, like if this is n vertices, this will give accordingly a less number of vertices, like n by 2 vertices. So here, if you see, after contraction, which graph I got, that is a non-bipartite graph. I started with a bipartite graph with a unique perfect matching. And after contraction, I got a graph which is a non-bipartite graph. Okay. And here again, I started with a bipartite graph with a unique perfect matching. But after contraction, you can observe that I got another bipartite graph. Okay. So if I consider the class of all bipartite graphs with unique perfect matching, and I look at after contraction how they are looking at, so they will be either bipartite or non-bipartite. So we can divide into 2 subclasses. So if I take all the graphs, so bipartite graphs with unique perfect matching, I look at the class of graphs for which after contraction the graph is becoming bipartite again. So that is one class. So in that class, what has been proved, so if you start with a connected bipartite graph with a unique perfect matching such that the graph obtained by contacting the matching edges is also bipartite, in that class, these conditions are all equivalent. Okay. So the reciprocal of the largest eigenvalue will be the smallest positive eigenvalue, and G inverse will exist and it is isomorphic to G. And G will satisfy property R, G will satisfy property SR, and G is nothing but a corona. Okay, and G must be already we have taken bipartite, so it's just a corona of bipartite. So all these conditions are equivalent. So if my graph is of this form that G is bipartite and with a unique perfect matching, and after contraction also it's becoming again bipartite, then the graph will satisfy property R if and only if it is a corona. Okay, so in this class, it's again coming as a corona graph. So this is about characterization, and some in other class also, as I told, after contraction, it may be non-bipartite. In that class also study has been done, but I'll not go for that. What I can observe is, in the classes I discussed, property R is implying property SR. Okay. So both are becoming equivalent. but whether this is true for any graph. So in general, whether property R and property SR are equivalent. So that was because we had not got any example of graph which was satisfying property R but not SR. That means multiplicity was differing for certain eigenvalue. That kind of example we had not got. So this is obviously one question, that whether property R implies always property SR. That means multiplicity is same. But this is not true. We got example. So this way the construction I can show you how. So we got also certain classes. So you take a path of order 4 and take another take another vertex here, okay, and then join them. Okay, so I started with a path of order 4 and I took a sorry, I am saying pendant. It's not pendant, singleton vertex or K1 you can think. So then join to the path. Okay. Now what you do is you just take another pendant and add here in this part. And then you take a path of order 4 and you join from this vertex to the vertices of the path of order 4, which are degree 2 vertices. So this way. Okay. You take another copy. In one copy, it will not happen. So another copy also you have to take. So this way. Okay. Now this graph, which I constructed, this is satisfying property R, but not SR. Okay, I have here colored the vertices which are reciprocal of each other. So 2 plus root 3 is reciprocal of 2 minus root 3. They are the pair. They have the same multiplicity, but here 1 plus root 5 by 2 is appearing, and its reciprocal is minus 1 plus root 5 by 2. And this these have a multiplicity like 2 and 3 respectively, so they are not matching. Okay. So similarly, these also here also you can see these two are not matching. So this is a graph which is not bipartite. Okay, you can see odd cycles are there, and this is not bipartite, but it's satisfying property R, and if it's not satisfying property SR. So property R and SR are not equivalent. Okay. So we got some non-bipartite example, and this is not the only graph. We can here I started with a singleton vertex, but here you can put a complete graph and you can do the same type of thing what I did. So like here, so start with a path of order 4 and take a complete graph. I took K3 and do the same thing, join first and put pendants to each complete graph part. And then you take a path of order 4 and then join. So this basically you take this one and attach here. So this graph, this is known as let's say this is G33 because I started with a complete graph, and for each one I am adding one copy. This will also satisfy. You can add more copies here, then also it will satisfy property R, but it will not satisfy property SR. Okay. So because the coefficient, the power of this factor, x square plus x minus 1, and that will be n more than this factor. Okay. So this construction will give you graphs with satisfy property R, but not S. Okay. So this is again a problem that characterizing all graphs like which are satisfying property R, but not SR. Obviously, so far, whatever we have done in bipartite class, we are not getting such example. So we assume that, or we are suspecting that in bipartite class, both the property will be equivalent. So property R will imply property SR, but it has not been proved yet. And such graphs which are satisfying property R but not SR, those are rare. If you look at this paper, like here the classes are given, but those classes are obtained in a way, like as I told, like I'm taking a path of order 4 and then attaching the copy. That way only obtained, and some other classes similar way can be constructed. But these factor, they are not matching. And here the roots, if you look at, those are basically root 5 plus 1 by 2 like that. So that eigenvalue is not matching. But we have not yet got different kind of examples or classes where this property R is there and property SR is not there. So if such graphs exist also, they are very rare. So to characterize graphs with property R, not SR, that is an interesting problem, but again, a harder problem. So, but one can look for. Oh, here I would like to say another thing that was that's a question one can pose again. So when we are defining property R or reciprocal eigenvalue property, in that case, we are taking non-singular graphs, okay? AG must be non-singular because we are looking for lambda and then 1 by lambda, okay? So I cannot consider 0 there. So our graphs must be non-singular in that case. But if I look for singular graphs, okay? So zeros are allowed. So some 0 eigenvalues will be there. Then we'll look for the non-zero eigenvalues and leave about the 0 eigenvalues. You have started with a singular graph, but leave the 0 eigenvalues. Now look at the other eigenvalues. That means all the other non-zero eigenvalues. Whether those non-zero eigenvalues, they are satisfying property R or not SR, that is a question. So can there exist a graph which has at least one zero eigenvalue, that means it's a singular, and whose non-zero eigenvalue, they are satisfying reciprocal eigenvalue property, that means lambda is an eigenvalue, then 1 by lambda is an eigenvalue. So such graph is there or not? Okay, so that's a question we consider it. So if such graph exists, we'll call it weak graph with weak reciprocal eigenvalue property. And the first example that is, you can observe this is K1. K1 has spectrum 0. So there is no other eigenvalue. So obviously trivially it's satisfying this property that is what I told, weak reciprocal eigenvalue property. So it's a trivial example, okay? It has no other eigenvalues or non-zero eigenvalue. But then we asked whether there is any other graph, means non-trivial graphs are there, or at least non-trivial trees are there. So the way we moved here, one graph product that is mostly useful is the direct product, or you say Kronecker product, okay? So that is like if you are taking two graphs with disjoint vertex sets, let's say U1 to UM and V1 to Vn. So for the product graph, the vertex set will be Cartesian product of these two vertex sets. So that is VF into VH. So the in the product, the vertices are just pairs of these vertices. So U1, V1, U2, U1, V2, like that. All the pairs you have to take as vertices. And two pairs, they are adjacent if the corresponding coefficients are adjacent in the respective graphs. Okay. So UI Vj and UR Vs, they will be adjacent in the direct product. If UI is adjacent to UR in your first graph and Vj is adjacent to Vs in the second graph. So if both the things are happening, then only you can put one edge here between these two pairs. Okay. So this is the direct product. I think many of you must be knowing. And in case of direct product, this was proved by Wessel that the direct product is connected, that is F cross S, that is connected if and only if both F and H are connected and at least one of them is non-bipartite. Okay, if both are bipartite, then you will get exactly two components. Okay, so the product will be connected if and only if both the graphs are connected and one of them must be non-bipartite. Okay. And if you are taking a direct product of a bipartite graph with any bipartite graph, it is always bipartite. And this is also you can find in this book that if you are, and you can prove easily also. So because you can write your adjacency matrix nicely. So if lambda1, lambda2 to lambda m are eigenvalues for the first graph F, and mu1 to mu1 they are eigenvalues for the second graph H, then their products, all possible products, lambda I mu j, those will be eigenvalues for the product, direct product F cross H. Okay. So eigenvalues are completely described, all the eigenvalues for the direct product in adjacency case. In Laplacian case, it's not done. Okay. You cannot describe all. So you have to assume both the graphs regular. But in adjacency case, nicely, all the eigenvalues you can compute using the eigenvalues of F and H. So they are just products. Okay, this I'll use. And then one thing here, you can observe that if F and H both are connected graphs, two connected graphs, then F and H satisfy property R implies that the direct product also satisfy property R. Okay, so this can be observed easily because the spectrum is this. But the converse is not true here, and you can get one example. So using the direct product, this we could prove, and this is a more stronger result, that if a graph is satisfying property R, then also the determinant will be +1 or -1. So here in case of property SR, multiplicity of lambda and 1 by lambda was same. So then the product was coming as +1 or -1. But here, even if the multiplicity is differing, then also when you multiply all the eigenvalue, that will give you +1 or -1. So if a graph satisfies property R, then determinant must be +1 or -1. And this has been proved nicely using this proof. I like that it's very nicely like this was a result that was means this was not like we were not suspecting that this will happen, but nicely this like we could prove this using direct product and in a very simple way. So let us start with a graph G. Okay, and that's satisfying property R. Okay, so let us take the spectrum as lambda 1 to lambda n. Now, suppose the determinant is not 1 or -1, so it will be some integer. Okay, so that will be because your matrix is an integer matrix, so determinant will be some integer, let's say m. Okay, so then you consider the direct product of G with itself n times. So take G, direct product G, direct product G like this. Okay. So what we have already proved means we show the result. When I'm taking G, direct product G, I know the eigenvalues, right? Those will be all product of eigenvalues of G with itself. So lambda 1, lambda 2, lambda 1, lambda into lambda 1, like this, all two products will be there. And when you will take another copy and multiply, then all three products will be there. So like that, I can say what are the eigenvalues of H. Okay. So you will get n to the power n eigenvalues, and those are of the form like lambda I1, lambda I2, lambda In. And I1, I2, In, they belong to this 1 to n. So all n times like products, though those will become eigenvalues for H. Okay. So in particular, so if I choose for the first copy lambda 1 and the for second copy lambda 2 and the last one for last one lambda n, so I'll get that lambda 1 into lambda 2 into lambda n, that will be one eigenvalue of H. Okay. And your G is satisfying property R. So if lambda 1 is there, then 1 by lambda 1 is also there. Lambda 2 is there, then 1 by lambda 2 is also there. Lambda n is there, then 1 by lambda n is also there. So you have also the eigenvalue because all these are present in G. So you have one eigenvalue of H that will look like 1 by lambda 1 into 1 by lambda 2 into 1 by lambda n. Okay, so this number 1 by lambda 1, lambda 2, lambda n, this is also one eigenvalue of H. But lambda 1 into lambda 2 into lambda n, that is m, that you are taking m. Determinant you are taking m. Okay, so 1 by lambda 1 into lambda 2 into lambda n, that is 1 by m. And that is becoming one eigenvalue of H. Okay, and H is a graph. And you got one number that is looking like 1 by m, and that's becoming one eigenvalue. But your polynomial, characteristic polynomial for H is just a polynomial which is monic with integer coefficients. In that case, obviously, every eigenvalue which is coming as a root of that equation, that must be, if it's a rational number, that must be one integer, right? So 1 by m, if it's eigenvalue, then it must be integer. That tells that your 1 by m is plus 1 or minus 1. Okay, that means your m is plus 1 or minus 1. So if the graph satisfies property R, then determinant must be plus 1 or minus 1. Okay, so this result we used to tell like about the weak reciprocal eigenvalue property. So here, like you can also have this remark that if you are taking a connected graph and if G is satisfying property R, then the last coefficient, that is plus 1 or minus 1. Okay. So using this result, we could prove that if you are taking a tree and it's a singular tree and it's non-trivial, that means n is greater than or equal to 2, then its non-zero eigenvalues cannot satisfy property, this reciprocal eigenvalue property. That means there is no tree, singular tree, which is satisfying the weak reciprocal eigenvalue property. So except your K1, that is a trivial case, there is no other tree which is satisfying the weak reciprocal eigenvalue property. Okay, so in tree case, such graph doesn't exist. Now, to move forward, like we thought that maybe in graph case it will happen. So we looked for the question that is there a non-trivial graph with the weak reciprocal eigenvalue property? So here again, we looked for this thing that if the graph is singular, then the obviously characteristic polynomial will look like this because some zero eigenvalues are there. So let's say n minus k zeros are there. So k is, I'm taking rank of AG. So then your n minus k eigenvalues are 0. So the polynomial will take this form that x to the power n minus k you can take out. And here this is the coefficient ak is the coefficient of x to the power n minus k. That is the non-zero coefficient you are assuming, the smallest non-zero coefficient. So let us take AG has rank k and I'm taking AK, that is non-zero. Okay, so we asked the question whether this AK can be plus 1 or minus 1. Okay, if it's a non-singular graph, obviously, as you observed, like if it's satisfying property R or SR, then your AN becoming plus 1 or minus 1. But when the graph is singular and we are looking for last non-zero coefficient, can it be plus 1 or minus 1? Okay. So this is the question. And because what we observed that we took many examples and what we observed that this number was coming and like for this example G1, you look at the polynomial. So your last coefficient is minus 16. Okay. And we looked for many examples and there we observed that this number is not becoming plus 1 or minus 1. It's taking some other number and that was proved. So has to be proved for bipartite case that if G is a connected singular bipartite graph and AG has rank K, then this last coefficient AK, which is non-zero coefficient we are considering because rank we are taking K, that cannot be plus 1 or minus 1. Okay, the proof is again using direct sorry, here we will not use direct product, but when we will go for non-bipartite, we will use direct product. Here the proof is done because you have taken a bipartite graph. So I just took a partition R and C, and this is the partition. Then your matrix can be written in this way. So B transpose 0, 0. So your first part contains P vertices, second part contains Q vertices that I am assuming. Then since G is bipartite, K is even, so I am assuming that K is 2R. Then the characteristic polynomial of G that can be written in this way because all odd coefficient, those will be 0. So like coefficient of all odd terms, those will be 0. So you will get like x to the power n a2 x to the power n minus 2 like this. And last coefficient that you are assuming ak, that is a2r basically. So that's non-zero you are assuming. So this is the coefficient. This is the characteristic polynomial. Now, if I look for, this is the characteristic polynomial of AG. Now, if I look for B transpose matrix, its characteristic polynomial will also take the same form. Okay, so observe these are B and B transpose. Okay, so the characteristic polynomial of AG is of this form. Now I'm taking B transpose matrix and its characteristic polynomial I'm looking at. This will take this form. And you can observe that rank of B is same as rank of B transpose, that is equal to R. So we looked for this polynomial actually. And then here if I look for the last coefficient A2R, so that is AK for your original polynomial. So that will be this, because you will take all R cross R principal sum matrices of BP transpose. So that will be this, and then you are adding. And then using Cauchy-Binet formula, I can write in this way. Okay. So here, because this is BST and B transpose ST, matrix is symmetric matrix, so I can just replace by square, determinant square. So you will get like this. And here one can observe, like you can go through the paper, I have less time, so I'll just conclude. So here you can observe that such type of matrices, like at least two matrices you will get for which the determinant will not be zero. You are taking sum over all such matrices, right? And you will get at least two matrices for which determinant will not be zero. So in that case, you will get that your A2R is at least 2, so or minus 2. So this will come out that A2R mod is greater than 1. So this way we prove that if you are taking any bipartite graph and its rank is AG has rank K, then this last coefficient cannot be plus 1 or minus 1. And that can be proved for any graph also. I gave the proof for connected bipartite. Now you take connected singular graph, so any bipartite or non-bipartite. Here also you can prove. And once we have proved for bipartite, I used here the direct product and I'm skipping the proof. But for any graph, this is true. Okay. So if it's a singular graph, then the last coefficient cannot be plus 1 or minus 1. And using this, we could prove this, that if G is a connected singular graph, then G cannot satisfy the weak reciprocal eigenvalue property. So there is basically no non-trivial graph for which non-trivial singular graph for which the non-zero eigenvalue they satisfy the reciprocal eigenvalue property. Okay. So this problem ended here, concluding, and then we looked for here one nice thing came out, one observation that I would like to say here, that this when we considered this singular graphs, that means AG is singular, and we took rank as K, and we looked for the last non-zero coefficient that was not plus 1 or minus 1. But this is our matrix is in that case a 0, 1 matrix, and it's a symmetric matrix, right? So, but what we observe that can be generalized to any symmetric matrix with integer entries. So if you take a matrix A and that has integer entries and rank of A, let's say K, and this is the extra assumption that you have to take, that A has at least K plus 1 non-zero rows. Then if the characteristic polynomial of the matrix is this, means rank is K you have taken, so it will take this form. Then this last coefficient cannot be plus 1 or minus 1. So this is true for any symmetric matrix with integer entries. And that's basically defined as pseudo-determinant. So if you are taking a matrix, singular matrix, and pseudo-determinant is defined as the product of all non-zero eigenvalues of A. So if the matrix is singular, then it will be like you are taking the, like what I told, the last coefficient in the characteristic polynomial. Okay. So this is the result. Then we can say that A is a symmetric matrix with integer entries, and rank of A is K. Okay, that is less than n. So the matrix is singular basically, because for non-singular case, this will not happen. So for singular, and then A has at least K plus 1 non-zero rows, then determinant or pseudo-determinant of A that cannot be plus 1 or minus 1. So this is one kind of one observation that we got, that is like we use linear algebra techniques to graph theory, but here from graph theory result you can conclude this is a good result for like matrices. So then we looked for whether, because there is no graph which is satisfying weak reciprocal eigenvalue property, so we could look for like, is there any weighted graph with the weak reciprocal eigenvalue property? Okay, so we constructed weighted graph putting edge weights. So you can take positive weights. Then what we got one example that if you are taking a tree and that is just a path, so put the weights like 1 by 4th root of 3. Okay, so the same weight you put to all edges. This graph has eigenvalues like these are the eigenvalues. So you can observe that this is a singular graph and it's at the non-zero eigenvalue, they are satisfying the reciprocal eigenvalue property. So this is a tree, weighted tree, and it's satisfying the weak reciprocal eigenvalue property. Okay, so we gave a construction also. So if G is a connected singular bipartite graph on n vertices and rank of G is 2 or 4, then the characteristic polynomial will look like this. So here you can assign weights, and the weights will be assigned in this way that if rank is 2, then you take the weights 1 by square root of minus a2 and put to all edges. And if rank is 4, then take the weight as this number and put to all edges. Then GW will satisfy the weak reciprocal eigenvalue property. So this is a class that has been given, but the characterization of all weighted graphs is again a like a question. But if you restrict your weights, those are all greater than equal to 1. So your weights are from 1 to like any large number, any positive number. In that case, actually this came out. This is again interesting that your weighted graph cannot satisfy weak reciprocal. And in tree case, weighted tree cannot satisfy the reciprocal weak reciprocal eigenvalue property. So if you restrict your weights as greater than equal to 1, then the weighted tree, which is singular tree, that cannot satisfy a weak reciprocal eigenvalue property. So you don't have any tree. So here I'll stop, and these are the questions I already pointed out while presenting. So one is characterization of unicyclic graphs with property R. That question is still open. Second is characterization of all bipartite graphs with property SR, at least property R. Like we are thinking that property R and property SR will be equivalent. So this question is again a problem to consider. And for bipartite graph, whether these two are equivalent, that is again to prove or disprove. Now, characterization of weighted graph with weak reciprocal eigenvalue property, that is also a question that has not been done. And the most important thing is like for property R, the reciprocal eigenvalue property, like you know that if in bipartite case, like the property is plus minus pairing, so that is like lambda is an eigenvalue, then minus lambda. And for such like property, the graph class is the bipartite graph class. And their bipartite graph class has certain other properties, like we know that has node, cycle, and other things. So the structural property of such graphs are known. Okay. Similarly, in tree case, if the graph is satisfying property R, there are other properties of graph that we know, like the number of alternating path is exactly 2k minus 1 that I told, and its inverse is isomorphic to itself. So like those things are known for tree case. But for graph case, if a graph is satisfying property R, then only we know that the eigenvalues will satisfy that property. But what other properties the graph is having, those are not investigated so far. So this is one of the question that how the graph structure would be in graph case, that is, or what are the other properties the graph is having when it's satisfying property R. Those are not explored, so those can be explored. And another property that was defined, like from our first result, you can see lambda is an eigen. If you are taking any corona, then lambda is an eigenvalue, then minus 1 by lambda is also an eigenvalue. So this reciprocal eigenvalue property, looking at that, one can define also anti-reciprocal eigenvalue property. That is, if lambda is an eigenvalue, then minus 1 by lambda is also eigenvalue. So then all the problems all the discussion that I did, those can be considered for anti-reciprocal eigenvalue property. Okay. So some work has been done by people, but one can look for this. Okay. Thank you. So I'd stop here. Any question you can ask.
We will stop recording.
Okay.